The takeaway here is that just by looking at the wave function, it's not obvious whether it's entangled or not. Simple example is if you look at this state, you have minus sign, this state is actually entangled. So like it's not immediately clear by looking at the wave function that the state is entangled or not, but there are ways to quantify it which I won't get to in this lecture. Any questions about that? So then let's talk about how to create these well states. So the question is, we want to start from a boring product state where the two qubits don't talk to each other and create something entangled like the bell state. To do this, we need some unitary operator that acts on both the qubits at the same time. So in the quantum information language, these are called two-qubit gates. And a classic example is the C0 gate, which acts on, I think it's called an input qubit and a target qubit. And this is the corresponding output. So this has the following relation. So if you've seen the C0 gate in your first semester computer science class, or second semester electrical, I forgot. But this is basically the classical C0 gate, but applied to quantum states. And I'll quickly show you how you can start from a product state and create the bell state. So the idea is to start from the following product state and apply C0. From qubit 1 to qubit. So this notation just means that 1 is the input qubit, which tells you whether you're flipping the second qubit or not, and 2 is the target qubit. So how does C0 act on this state? So this state can be written as 0, 0 plus 1, 0. Not going to worry about normalization. Is that okay? And since this is a linear operator, we can simply act on them separately and just take the sum. 0, 0 goes to 0, 0, but 1, 0 goes to 1, 1. And this is the bell state. Is that clear to everybody how you construct the bell state starting from a product state? The intuition is the following. Two qubit gates can create or destroy entanglement between neighboring qubits. So that's essentially what we are doing. We are starting from a state with no entanglement, applying a two qubit gate. Gate just means unitary operator, nothing more than that. And that effectively creates entanglement between these two qubits. I also want to tell you about another way to create the bell state. Using measurement. So I hope everyone is familiar with quantum measurement. What quantum measurement does is that it projects your quantum state into an eigenstate of the measurement operator, or whatever operator you're measuring. Plus, it gives an output which is the corresponding eigenvalue of the operator that you're measuring, right? Traditionally, we think of measurement as something we do to get information about our quantum state. the theme of this talk is that you can also use it as a dynamical process. The process of collapsing a wave function can be used to create more interesting wave functions just by itself. And getting the eigenvalue is sort of a secondary aspect of measurement. Okay? So the way to create a Bell state using measurement is to start from a generic 2-qubit state. And measure the following operators. These two operators. So you measure x1, x2 and z1, z2 at the same time. And we can measure these two operators simultaneously because they commute. Commuting operators can be measured. So, I forgot to mention this. When we measure x1, x2, what are the possible eigenvalues that you can get?
0 and 1.
0 is not possible, right? So x1 has eigenvalues plus 1 and minus 1.
Okay.
x2 has plus 1 and minus 1. So their product can only have eigenvalues plus 1 or minus 1. So there are 4 possibilities when you measure x1, x2 and z1, z2. So I'll write them down.
Sir, could you please mention what do you mean by measuring an operator?
So this is from quantum mechanics. The idea is just like you measure the position of a wave function, you collapse the state to a delta function at that position, right? You can do this with any Hermitian operator. So what happens when you do that is the state collapses into an eigenstate of the operator that you're measuring, and the output that you get from the measurement is that state plus the corresponding eigenvalue. That's what your measurement apparatus will tell you. And just fill this table up, it will be clear what I mean. So I just explained now that these two operators can only have eigenvalues plus 1 or minus 1. So there are 4 possibilities. Then you get 1, 1, 1 minus 1, minus 1, 1, or minus 1, minus 1. And this, you have to do this calculation. I'll just tell you the answer. If the state is eigenvalue 1 for both of these operators, then the state has to be 0, 0 plus 1, 1. Right? Because if you apply x1, x2, it's flipping both the states, so it goes to itself, which means the eigenvalue is 1. If you measure z1, z2, it just measures whether the state is in upstate or downstate, and 0, 0 gives eigenvalue 1, 1, 1 also gives eigenvalue 1 because it's 2 minus 1. You can do the same thing 4 times. You'll find that this has to be 0, 1 plus 1, 0. This has to be 0, 0 minus 1, 1. This has to be 0, 1 minus 1. Maybe it's not immediately obvious, but is the general idea clear that you have to get the right eigenvalues, so these are the only 4 possibilities. Okay? So then I have this step called post-processing. The idea there is that I want to create a particular Bell state, this one. But I only get that for a particular measurement outcome. I don't get it for any measurement outcome. And in general, I don't have control over what measurement outcome comes out. That's just random. So what we do is we apply another unitary operator that's conditioned on the particular measurement outcome that we get. So if my detector reads that I got eigenvalue 1 for this and 1 for this, I don't do anything. So my post-processing is just 1. I don't apply any unitary operator. But if my detector tells me that it measured 1 for this operator and minus 1 for this operator, I just apply x1. And when I apply x1 to this state, you can see that this becomes 0, 0 plus 1, 1. Is that clear? Similarly, you can show that I can apply Z1 to the state and it goes to the same state. And this one, X1, Z2, will give you the required output. So post-processing is important in general when you use measurement to create states because you don't have control over which state it projects into. So generically you have to apply some additional unitary operator that's dependent on the particular measurement outcome that you take. Okay? Any questions about that? So this was the quantum information introduction. Now I'm going to get to a condensed matter topic, which I find more interesting, hopefully you will do. This is called the quantum Ising model. So the setting is the following. Before I get there, are people familiar with the Ising model, the classical Ising model? Yes? Basically, nobody. You don't need to know the classical Ising model to know the quantum Ising model, but people are familiar with Hamiltonians, ground states, and so on, right? So if I have 5 qubits and I give you a Hamiltonian, you know how to find the ground state. You can write down the Hamiltonian, you know how to diagonalize it in Mathematica. So the system is the following. You have n qubits arranged on a ring, also known as periodic boundary conditions, if you are a condensed matter person. So just imagine you have, so each dot represents a qubit, and the Hamiltonian is, there is a nearest neighbor term, and there is a, what's known as a transverse field term for historical reasons or experimental reasons. It's not important, the name is not important, but I'll tell you what these terms are trying to do. Let's think of the states in the Z basis. What this term is trying to do is that there is an energy cost if the neighboring spins are pointing opposite to each other. Right? Is that here? Zi and Zi plus 1 are pointing in opposite directions, that's an energy cost. So we want to lower energy, so this term doesn't like having an upspin next to a downspin. Whereas what this term is trying to do is it wants all the states to point in the plus direction, because that's the plus 1 eigenvalue of the x operator. Another way to think of the plus state is it's a superposition of 0 and 1. So in the 0, 1 basis, what this operator wants to do is it wants the state to fluctuate. It wants the state to form a superposition of up and down. Whereas this state wants the qubits to either be parallel or anti-parallel. So it's a competition between these two states. This state wants the qubits to stay parallel or anti-parallel. This state wants the qubits to fluctuate around with each other. So you'll see that this Hamiltonian, as you vary this real parameter h, has a non-trivial behavior. So if you end up studying condensed matter, this will be your bread and butter. So yeah, you can write many papers out of this. So before I describe the physics as you vary this parameter h, I want to mention that this Hamiltonian has a symmetry, which I will denote by G, which is simply the product of all the x operators. Okay, so we say a Hamiltonian has a symmetry if the symmetry operator commutes with the Hamiltonian, right? It's obvious that this operator commutes with this part of the Hamiltonian because it's just x. Does this operator commute with this part of the Hamiltonian? Yes, because Flips everything. Yeah, that's a good way to think about it. But can you relate it to the earlier discussion?
Because it will change the sign 2 times.
Exactly. So, whichever location I you choose, Zi will anti-commute with this. Zi plus 1 will also anti-commute with this, so it anti-commutes twice, therefore it commutes. But what we said is the more physical way of thinking about it. This operator flips all the spins in the Z basis, so that should not change whether two nearby states are pointing along each other or opposite. Okay? And one thing you know if you have studied quantum mechanics is that if your Hamiltonian has a symmetry, you can diagonalize in the symmetry sectors, different symmetry sectors, and diagonalize the Hamiltonian within those symmetry sectors. So we take that approach, and so what eigenvalues can this operator have? Plus 1 or minus 1, because it's just products of all your operators. So we will work. So we will ignore any states in our Hilbert space which has G equal to minus 1, and we will simply work in this sector. So is that clear to everyone? I can remind you where the quantum mechanics idea comes from. So now that we have that, let's draw a line which represents the value of h here.
Why specifically are we only restricting ourselves to G equals plus 1 eigenvalues?
That's a good question. The answer is obvious in hindsight, but now you just have to play along with me. I can tell you at the end of the talk. For now, a reasonable answer is we want to simplify the problem, so it's useful to work in a particular symmetry sector. Why I chose plus 1 over minus 1 is slightly non-trivial. Maybe you understand it towards the end. Okay. So this is h equal to 0. This is h equal to infinity. Then let's look at what the ground state looks like at each of the two ends. Okay. So let's look here. When you have h equal to infinity, this term is dominating. This term you can ignore. Basically, this term is dictating what the ground state should do. This term basically has no say in the matter. So I want you to tell me what the ground state looks like in the h going to infinity limit. Yeah, exactly. So it wants to make this term happy. So basically, every qubit is independently pointing in the plus direction. And you can denote the state in the following. So, what about this end? Set this operator to 0. What is the ground state of this problem? Everything is in 0 or everything is in 1. So there are two possibilities. So, but I said something earlier that we will work in the G equal to plus 1 sector. Right? So these two possibilities don't independently occur. There's only one possibility, which is 0. That's something. The 0 1, does it satisfy G equal to plus 1? No, it doesn't give you. It's not an eigenstate of the symmetry operator, right? Because x flips into. So the only possibility is this. All 0 plus all 1 in this particular superposition. Okay. So this state has many names. It's sometimes called a GHZ state. Sometimes called a CAP state. So, from the title of the talk that you got in the email, can you tell me why this state might be called a CAP state? So, how does it relate to Schrodinger's CAP?
Because it's in measurement 0 plus 1.
Exactly.
So it's
It's
both
called a
things
CAP
are
state because it's in a macroscopic superposition. In the sense that you have some very large system which is either dead or alive, which are very different states, but it's in a superposition of these two very different states. as you can guess, this is the state that we'll try to construct today. Okay. So there's some interesting physics because the state has this particular structure, and this relates to what's called spontaneous symmetry breaking. So imagine you have this particular setup, either in a solid state system, like some material that you grew in the lab, or you simulate this on your quantum computer, and you somehow prepare the ground state. So if your Hamiltonian is exactly symmetric, and you start from a symmetric state, g equal to +1, the state that you obtain is this. It will still remain symmetric. But this state is very flimsy, in the sense that any noise from the environment, imagine the environment is some kind of classical observer, it will immediately collapse the state into either all 0 or all 1, just like Schrodinger's cat. So what happens in the lab is that when you try to prepare the state, because of environmental noise, it immediately goes into all 0 or all 1, which is a state that's not symmetric, right? This basically called spontaneous symmetry breaking. It's a very fundamental concept in both condensed matter and high energy physics. That's a lot of words, but I hope you got the intuition behind it. And in fact, you can show that what happens as you vary the parameter h, that there is a very sharp transition. When h is less than 1, everywhere you have some ground state that has GHZ type structure, in the sense that any symmetric ground state will be in a macroscopic superposition state, much like Schrodinger's cat. Whereas if h is greater than 1, it will be in some kind of product state or something close to a product state, which I'll just call it trivial. And if you're interested in how to find this transition exactly, there is a map called the Jordan-Wigner transformation. You'll probably learn this in some graduate level course. That can be used to exactly solve this problem, like analytically without any help from computers. Yeah.
So when you're saying the GHG type structure, like will some of the zeros they'll be replaced by ones or something like that?
It's slightly more complicated than that. It's basically going to be some. So you can imagine starting from this state and adding some local spin flips fluctuations and some local superposition of the 0, 0, 0 state. So maybe something like 0, 0, 0 plus a spin flip here, plus a spin flip here, and so on. But basically something that looks like a 0, 0, 0. Plus its spin flip copy. So it's something that roughly looks like all spins are pointing up, plus all spins are pointing up. But when h is greater than 1, it's completely different. It's qualitatively different. There's only one ground state. And yeah, is that clear? So yeah, this has many names. This phase is called a ferromagnet. And this phase is called a paramagnet. This is again for historical reasons. But maybe you can think of it as ferromagnet is when all spins are pointing up or down together. This is also sometimes called a SSB phase and trivial phase. SSB just stands for spontaneous symmetry wave. Okay? So that's the first major physics idea that I wanted to convey. Is that clear? So then I want to ask the following question. The GHZ state looks slightly special. It's not as simple as a product state, it's a sum of two very different product states. Can we create this state starting from a product state and using local unitary gates? So I'll write that down. So by local, I just mean that if I'm applying a 2-qubit gate like a CNOT operator, it can only act between site I or I plus 1 or I or I plus 2, but it can't act between site 5 and site 20. Like there's some limit in the local sense where it can act. And the claim is that, which I won't prove today, but you can prove it, you can find in literature, is that you cannot do this in finite time. So I'll explain what that means. Say if you wanted to do this, the way you would do this is the following. You start from product state, which is so these are your n qubits, which is initially in product state, where the first state is a plus state and everything else is a 0. Then what you would do, you would apply a sequence of gates like this. I'll explain in a second what this means. This is the time direction, and this is space, and this is the CNOT gate. So this is the input qubit, and this is the target qubit. And just draw an arrow here to denote which is the input and which is the target. So let's see what the state looks like at each step. So if you look here, I explained earlier that if you apply a CNOT gate on a plus times 0, you get a Bell state, right? Plus is 0 plus 1, and the 1 flips the next 0, so you get a 0, 0 plus 1, 1. So here it looks like 0, 0 plus 1, 1. And now in the next step, the second qubit acts as the control qubit for the third one. And you can show that at this step, you have something that looks like 0, 0, 0 plus 1, 1, 1. Right? And you can see that as you repeat the process, n times, you get the GLC state. But from my point of view, I don't consider this an efficient process because the time it takes to do this scales with the system size. So when I say efficient or finite depth, I mean that the time it requires to prepare the state should not scale with system size. That's what I mean by finite depth. So I just gave you an example of how to create the GNC state in linear depth, linear in system size. But the general claim is that you cannot create it in finite depth. But I will not prove that today. But hopefully this is intuition enough that you need linear time because you need to create some macroscopic superposition. The surprise is that if you use measurements as the dynamical process, you can create it in finite time, which is what I tried to explain. Any questions about that? So before we go there, I want to teach you some more interesting condensed matter physics, but hopefully it's also useful if you're interested in other things. I want to explain a very deep concept called duality, which will show up if you go into either condensed matter or high energy physics. It shows up in gauge theory, it shows up in string theory. I heard that it also shows up in Langland's program, if you know what that means, but I have no idea what that means. But it's a very nice, simple concept, which I can explain to you. So stop me if something is confusing. This just stands for quantum Ising model. And we'll restrict it to the particular symmetry sector G equal to plus 1. Then I want to define some terms. I'll define what I call charge. So, charge is what is measured by the symmetry operator, essentially. The historical reason to call this charge is because whatever the symmetry operator measures is conserved, and we are used to the fact that charge is conserved. That's basically it. So I'll give you an example. Take the following state. What charge does the state have? Plus 1.
Plus 1, yeah.
So, if you're okay with a little bit of abstraction, I will call the plus 1 sector as 0 charge and minus 1 sector as 1 charge, and we'll talk of charge as modulo 2 objects. So, charge 2 is like charge 0, charge 3 is like charge 1, and so on. So, this is charge 0. This is charge 1. And this is the global charge. We can also think of charge as a local quantity because our symmetry operator is essentially a product of on-site operators. So in that language, I would say this site is not charged, whereas this site is charged. And charge is a Z2 object, modulo 2 object. So if I have two charged objects right next to each other, the total thing behaves like no charge.
Could you repeat how you measured the charge for the first state?
Right. So the charge is measured by the symmetry operator, and the symmetry operator is the product of all x's. So here, if you multiply the product of all x's, you get plus 1, right? And here you get minus 1. But I want to use a different, more physical language, where I call the plus 1 sector as charge 0, and minus 1 sector as charge 1. I'm just using modulo 2 addition instead of plus 1 minus 1. And the reason I want to do that is I want to count charges. Like, so this thing has 1, 2, 3, 4 charges, but 4 is equal to 0, so it's 0 charge. And this thing has 3 charges, 3 is equal to 1, so it's 1 charge. Okay? And charge is conserved because symmetry.
Why exactly are we shifting into an abstraction like 0 and 1? Like, does it offer any particular advantage? For example,
No, I
computation.
mean, it's just language. I've grown to be used to it.
I mean, does it, for example, offer any advantages in computation? Because it's again based in. So
No, not
is-
really. Yeah. So, in some sense, this is the right language because I've been a little sloppy when I said charge is what is measured by the symmetry operator. The technical term is charge is the operator that generates the symmetry. So, if you're familiar with generate, like the Hermitian operator generates a unitary operator, and you'll find that the Hermitian operator that generates the unitary operator G will have eigenvalue 0 or 1. Okay, so like, I'm being a little sloppy. So, yeah. Any other questions? So, what I call the G equal to plus 1 sector is basically saying the charge 0 sector. It's the same thing. Now let's look at the physics of the transversal Ising model, quantum Ising model. Sorry. Near h equal to infinity. Okay? So we know that at h equal to infinity, the ground state is just all plus, so no charges at all. So let's tune h slightly away from infinity. What happens is that this term starts to compete for energy. So like earlier I told you that there's a competition between these two terms. Initially I explained it in the C basis where this thing wants to align the spins and this thing wants to fluctuate the spin. Now let's think in the x basis because that's more convenient near h equal to infinity. This thing wants to align all the spins in the plus direction, Whereas what this does is it creates pairs of spin flips, right? It flips two spins at the same time. So the ground state now looks like it's very close to the original ground state, but it's slightly perturbed because and there's a small coefficient here, right? So do you get the idea? The ground state at h slightly away from infinity will not be simply this thing. It will be slightly perturbed away by the zi plus 1 operator, which tries to create pairs of spin flips in the x spaces. Is that clear? Okay. But importantly, all of these states will have total charge 0 because that's a symmetry of a state. If you look at this, there's a pair of spin flips, so it's charge 0. The symmetry is still satisfied. Okay. So if you're okay with that, next, let's talk about near h equal to 0. So here it's more convenient to talk in the z basis. So, and I'll introduce possibly a new concept, which is the idea of a domain wall. So a domain wall, if you've ever seen illustrations of a magnet, is a separation between an up region and a down region. So if I have a state that looks like 0, 0, 0, 1, 1, 1, 0, 0, 0, I will say that there's a domain wall sitting here, and there's a domain wall sitting here. Is that clear? So domain wall is just a separation between an up domain and a down domain. But in the quantum Ising model, domain walls cost energy because the zi plus 1 operator is essentially asking you whether there's a domain wall between I and I plus 1 or not. So in some sense, it's a physical object. Like it's like a particle that costs energy, which can move and so on. So it turns out near h equal to 0, it's useful to think of the state in terms of domain walls. We know that the exact ground state is all zeros plus all 1. But similar to this, when you add a small h, the x term tries to flip a single spin in the z basis, right? So the new ground state will look like this plus some small coefficient, maybe 1 spin slip. Basically, exactly similar to this idea. What the x operator tries to do is flip single spins one at a time, and that will give you a new ground state that's close to the original GHZ state but slightly fluctuating. So, to your earlier question, the ground state will look something like this. All these waves will be really small. So, state is basically the same as this in some post-gradient sense, but it's more complicated. Okay, so
he was saying that this is macroscopically aligned because this is the zero magnetic direction.
exactly, yeah. So it might be confusing whether it's aligned up or down. So for that you have to remember that this is the Schrodinger's cat state. When you actually have a real system, it will collapse into either this sector or this sector. So in that sense, macroscopically it will either point up or down. Okay. So here, instead of thinking of the spins themselves, let's think in terms of domain walls. So here it's like there are no domain walls. So maybe I'll use dot for lack of domain wall. And here there are domain walls. There are domain walls between the second and third it's basically a different representation of the same state, not in terms of the microscopic real objects which are the spins, but in terms of some new emergent object which is the domain. Now if you think of these states in terms of the domain walls, this looks very similar to what I wrote here. Right? Because here there are no charges. Then we have some states which have pairs of charges nucleated from the vacuum. Here you have something very similar. The main state is the one with no domain walls. But then you have some states with very small weight which have pairs of domain walls nucleated from the vacuum. But this is very surprising because you're talking about very different Hamiltonians. One is near h equal to 0, one is near h equal to infinity. So this suggests a deep relationship between these two Hamiltonians, which is called duality. The idea is that if you replace charges and domain walls, the physics near h equal to 0 match the physics near h equal to infinity. So I'll write that down.
Does this have some comparison between the magnetism and electricity?
Yeah. So I mentioned that in a second. So this turns out to be an example of what's called S duality in current literature. The S stands for strong to weak duality. This tells you that the weakly interacting regime h equal to 0 maps to the strongly interacting regime h equal to infinity. And there are many examples of such S dualities. One example, in fact, is actually electromagnetic duality, where you can replace electric fields by magnetic fields and electric currents by magnetic currents and so on. But there are much more complicated examples. In the 90s, string theory used to be full of these S dualities. But fundamentally, it's a very simple idea that you can trade in your microscopic degrees of freedom, which are the charges, for some emergent degrees of freedom, which are the domain walls. And they, in some way, behave the same way in different regimes of the problem. And fundamentally, the physics near h equal to 0 is the same physics at h near infinity if you just make this transformation.
So I think this problem. So what happens in the Lagrange program is that there are two separate theories. Very broadly, you could look at it something like an automorphic theory and there's a spectral theory that happens. So lots of algebraic geometry, lots of representation theory will happen. And there's a correspondence between this. So what you're trying to prove is that some mathematical objects are equivalent. And what this duality here, so if you're looking at the duality between electricity and magnetism, or electric fields and magnetism, whatever, what happens in the Lagrange program, very, very broadly, is that you are looking at it, an automorphic theory and a spectral theory, trying to prove the equivalence. Now, the world is your oyster, go explain.
So right now I simply drew some pictures and told you that this is the same physics, but in fact we can make this exact. And the way we will do it is by writing down an explicit unitary transformation that takes the ground state near h equal to 0 to the ground state near h equal to infinity. And since it's a unitary transformation, it automatically tells you that the spectrum of the Hamiltonian is the same. The energy to excited to the first excited state will be the same. So basically all the physics is the same if you make the trade between charges and domain walls. Okay? And you know that a unitary operator can be defined by its action on a set of orthonormal basis elements. I'll do that. And the action is essentially motivated by the trading between charges and domain walls. I'll call this UKW. Forgot to mention, this specific realization of S duality is called Kramer's one-year duality. You will probably see this in your SAPME course or some quantum many-body course. Because of Kramer's in 1 year, I'll write this as UKW. U denotes that it's a unitary operator. So, is the general prescription clear? Maybe I'll draw one more example. So, is the general prescription clear? If I have a charge at side 3, I put a domain wall between 3 and 4. If I have a charge at side 4, I put a domain wall between 4 and 5. And I also keep the symmetric copy, like I apply the symmetry transformation and keep the copy version as well. So on this side, we are always in the G equal to +1 sector, because G acting on this will produce this, G acting on this will produce this, so it's always in G equal to On this side as well, we are always in the G equal to +1 sector, because G equal to -1 means you have an odd number of charges. But that's not consistent because you cannot have an odd number of domain walls. Because you have periodic boundary conditions, the number of domain walls will always be even. So this is a unitary operator that acts completely within the G equal to +1 sector of the full Hilbert space. Okay. And because it takes a charge at side I to a domain wall at side between I and I+1, you can explicitly show that under conjugation, it satisfies this, because charge, an operator which measures charge is xi, maps to the operator which measures the domain wall, and a slightly more non-trivial relation. Can anyone tell me what this might be? So the way to think about it is that what does Zi plus 1 do to in the charge basis? It creates two charge flips, right? So whatever operator comes here should create two domain walls right next to each other. And this is creating a charge at sites I and I+1, which means that it should create a domain wall between I and I+1 and I+1 and I+2, which means that it should be xi+1, right? Does everyone understand why it's I+1? So what you see is that
Could you repeat the charge cycle?
Yeah.
Like Zi plus 1 is creating two charges.
right, because Zi flips in the X basis, right? So it creates a charge at I and it creates a charge at I+1, right?
So how many domain walls will you have?
So in this map, charge at I maps to a domain wall between I and I+1. So if you have charges at I and I+1, you have a domain wall between I and I+1 and also between I+1 and I+2, right? But now you imagine you have a ferromagnet. You want to create two domain walls, one between I and I+1, one between I+1 and I+2. You do that by simply flipping the spin at I+1, right? Because then you have a domain wall here and a domain wall here. That's why this has to be xi+1. Okay? And now that we see how the operators transform, we can look at the transform Hamiltonian. I erased the original Hamiltonian, but hopefully you remember it or you have it in your notes. It was Zi plus 1, which we argued that maps to xi plus 1. And it was xi here, which maps to zi plus 1. So this is equal to h times that last step here. So if we ignore an overall constant in the Hamiltonian, which doesn't change the ground state nature of excitation, etc., only scales all the eigenvalues, which we don't really care about. What this unitary operator does is that it tells you that the spectrum for a theory at the value of this parameter h is equivalent to the spectrum at 1 by h. So it maps the theory at h to a theory at 1 by h, which tells you that this is a strong to weak duality. So like when h is large, it maps to a theory where h is small, and vice versa. Yeah, so I had a pop quiz here, but in the interest of time, I will just give it as a homework. Maybe it's immediately obvious to you, but recall that. So, what this tells you is that h goes to minus h, these two theories have the same spectrum. Which also means that the theory is at h equal to 0 has the same spectrum as the theory at h equal to infinity. But I told you that when h is less than 1, there are two ground states. There's an all up state or something similar to that. There's an all down state where something similar to that. But when h is greater than 1, there's only one ground state. Now I'm telling you that there's a unitary operator relating these two Hamiltonians. There's something missing there. You can figure that out on your own. If you look carefully at all the steps that I mentioned, it should be clear. If you don't get it, feel free to email me. Or even better, discuss it among your classmates. Yeah. So I've introduced you to this very fancy technology. Ultimately, we only want to create this state, all 0 plus all 1. But I teach you a way to do this entire unitary transformation. So any input state that you give, it will give the corresponding output state. Ultimately, we will only use this product state to create the depth. To do this, we have to use this special short-range entangled state called the cluster state. I'll introduce this to you. This might be a difficult thing, so stop me at any point. So this is defined on 2n qubits. So you have twice the number of qubits. So n is the number of qubits you want to create the Bell state in. So we start with the cluster state on 2n qubits. And the wave function of the cluster state is the following. Let's write CS. Might not be immediately clear what the prescription is. The idea is the following. So you keep the odd sides in the 0, 1 basis, you keep the even sides in the plus minus basis. You form an equal weight superposition of all possible states in the 0, 1 basis. Okay? And the prescription for the plus and minus states is that if there is a domain wall between 0 and 1, it's a minus. If there is no domain wall, it's a plus. So here it's 0, 0, so it's plus, 0, 1, here it's minus. Then you simply write down all possible states and form an equal weight superposition of that. Okay? It might not be immediately clear, but this state is short range entangled. And I will sketch how you construct the state using a finite depth geometry.
Could you please explain this once again, like how this is functioning?
Right. So the definition of the state is the following. You take the odd sides, you basically form an equal weight superposition of all zeros and ones. But the even sides, the state of the even side is conditioned on the state of the odd sides in a way that if the two sides next to each other are the same, either both 0 or both 1, then it's a plus. If they are opposite states, then it's a minus. Then you simply follow this prescription, write down all possible states, form a superposition. Okay. The way to form the state is to do the following. So imagine these are your 2n qubits. You start from the plus state everywhere. And now think of the odd sides. Replace the plus by 0 plus 1. It's the same thing. Right? And I'm not doing anything, just a different way of writing the plus state. And then apply something called a CZ gate. This is a cousin of the C0 gate. What happens in the C0 gate is that if the input state is 1, you flip the output state, right? CZ is the same thing, but instead of flipping, you apply Z, which in the X basis is like flipping, right? Don't use.
Could you explain this schematics?
Yeah, so you start, so each dot defines a qubit, and you start from the odd plus state, right? And I choose to represent the odd qubit in a different way, just by definition plus is like 0 plus 1, right? Then what I do is I apply the following unitary transformation, which is a CZ gate, going from this as the input qubit to this as the target qubit. Okay. So let's focus on this part for now. Just these 3 qubits. What do these 2 CZ gates do? After the application of the CZ gate, there are 4 possibilities. Right? So you have 4 different superpositions here. The CZ gate will flip this pin in the X basis if this is 1. Right? So if both of them are 0, it simply remains plus. Is that clear? If this is 1 and this is 0, this doesn't do anything, but this flips it. You get a minus. This is 1 and this is 0, it's the same story, just flip it around, you get a minus here. Both of them are 1. This flips it, this also flips it, so it just goes back to plus. So this gives you the right prescription that I told you earlier, that you want a minus if there's a domain wall between the edges. Okay. Now there is a caveat here. Something slightly important is that all these 2 qubit gates commute. So earlier when I told you about the way to prepare a GNC state, I had to do it in a sequential manner. I had to do this first, then this first, then this first. That's because all of them did not commute. Because the target qubit of the first C0 gate was the control qubit of the next C0. because that changed it. You have to do it in a particular order. That's not true here. The target qubit of none of the CZ gates are the control qubit of any other CZ. Turns out that doesn't matter, but that's an easy way to understand why all these operators come here. And because of that, you can do it in any order that you want. And I choose to do it in this. In this fashion. So it just takes 2 rounds of unitary operators and done. All this is to tell you that the cluster state can be prepared efficiently simply using unitary operators. Not just unitary, local unitary operators. Okay. I did not emphasize this earlier. The local unitary is important because finite depth local unitary operators by definition preserve long-range entanglement. So the definition of long-range entanglement. Did I define long-range entanglement? No, right? Okay, sorry. I should have done that when I mentioned GHC, but I'll do that now. So this is an example of a short-range entangled state. The definition of short-range entangled, I usually write it as SRE, is any state that can be prepared starting from a product state by a finite depth local unitary transformation. So the number of layers of my circuit, this is called a circuit, does not scale with system size. Okay? So the cluster state is an example of a short-range entangled state, whereas the GHC state is not. For the GHC state, the circuit time scale with system size, so it's an example of a long-range entangled state. Is that clear?
Why doesn't this scale with actually?
What?
Why doesn't this scale with the number of qubits?
This one?
Yeah.
Because I just need 2 steps, right? I can do the process parallelly on all the qubits, whereas that's not possible for the GHC state. I have to do it sequentially. This idea comes a lot if you look at its matter, because in some sense short-range entangled states are boring, long-range entangled states are interesting. Shows up a lot. Yeah, if you have any questions? So, getting to the last part of the talk. Now I'll show you how to perform the Kramers-Wanier duality using the cluster state. The idea is the following. You start with the cluster state on 2 n sides, and you take your input state on n sides. So this is cluster, this is input. What you do is you measure these pair of qubits in what's called the Bell basis. I did not use this terminology earlier, but Bell basis simply means measure x1, x2 and z1, z2. Okay. What this does is it projects you into one of the 4 Bell states, 0, 0 plus minus 1, 1, 0, 1 plus minus 1, 0. And generally we can't control which state it projects into. It's random, the measurement outcome. I will work out the case where in all of the measurements, I get plus 1 eigenvalue for 2. I'll comment about the general measurement outcome case at the end, but if you want, you can work that out on your own. Okay? So, I choose the measurement outcome. +1 +1. This means that this state after measurement has to be the 0 0 + 1 1 state. Right? Another way of writing the 0 0 + 1 1 state is in terms of the x cases, is plus 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 minus minus. You can easily see that these two are the same because if you add x1 x2 on this, it gets +1, z1 z2 also gets +1. So let's see. Let's assume that we get this measurement outcome for all the cases, all the measurements, and see what happens for a particular input.
Could you repeat what you wrote in the last slide?
What I wrote in the book?
What you wrote in the last slide and
This one? Chosen measurement outcome, +1 +1.
and then the states.
Oh, if it's a +1 +1 outcome, then these two qubits after measurement will be in the 0 0 + 1 1 state, which is equal to the plus 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 minus minus. You can expand this out and see that they're the same, or you can see that this state has eigenvalue +1 under both of them, so it has to be the same. So I will not start with the general input state and see what comes out of it. That's too much algebra. Let's start with the specific input state, see what comes out. Then we'll invoke linearity to argue that for a general input state, it should give you the Kramer's one-year URL. Okay? So let's choose a particular input state, which is plus, plus, minus, plus. Oh, this wasn't the plus, minus, minus, plus. I want to be in the even sector, so I cannot have a single minus. So, and the cluster state on these sites let me expand it out. Basically, it's all of these superpositions, right? It's like these zeros and ones can take whatever values they want, and the in between sites will be plus or minus depending on whether there's a domain wall there or not. I forgot to introduce a word. This is sometimes called a decorated domain wall construction. It's a fairly new term. I like this word because it's immediately clear what we are doing. We take one subsystem and we decorate the domain walls of that subsystem with the charges of the other subsystem. So you put charges on the domain walls, it's called a decorated domain wall construction. But yeah, so if you write down a decorated domain wall for the cluster state, it's all possible states for the zeros and ones here with the corresponding value of the other state depending on whether there's a domain wall or not. And if you start from this particular input state and you have this measurement outcome, basically what it does is when you take the inner product, the only thing these qubits can do is if this being plus or minus matches whatever this is, right? Because this is projecting to a plus 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 minus minus state. So if this was a plus state, this also gets projected to a plus state. That's what the measurement outcome is telling. Okay? And we know that if this is a plus state, we project to the case where this is a plus state. This is a minus, we project to the case where this is a minus. This is a minus, we project to the case where this is a minus, and so on. We are left with two possibilities.
So we are basically mapping our input state to one cluster state.
No, that's not what we're doing. So what we're doing is we take the input state and we measured a subset of the cluster state along with the input state in the Bell basis, and we use these remaining qubits as our output. The remaining qubits are in some non-trivial state, which we'll take as our output. And the claim is that for any given input, these post-measurement form the Kramer's one-year dual of this input state. And maybe it's clear already in foresight because of the decorated domain mode construction. The decorated domain mode tells you that the charges tells you whether there's a domain mode here or not. So if I have a charge here, that will automatically mean that there's a domain mode here, which is essentially the Kramer's one-year duality. Is that clear? I have 7 minutes left. Okay, so what happens is that because I'm projecting to this particular measurement outcome, I have to throw away most of my cluster state terms except the ones where the intermediate charges match the charges in my input state. So whatever remaining qubits are there from the output state will be supposed to be 0, 0, 1, 0 plus 1, 1, 0. And that's because my input state was plus, minus, minus, plus. So plus, minus, minus, plus tells you that there's a domain mode sitting here and here, which means that it has to be 0, 0, 1, 0 plus 1, 1, 0, 1. So I calculated it for a particular input, but for a general input you can invoke linearity. And since for this particular input it realizes the charge to domain mode transformation, which is the Kramer's one-year duality, for any general input, let me write this. This is UKW acting on plus. Simply because everything is linear in everything I've talked about. So that's the main technology that I wanted to introduce to you. To summarize, the steps involved where 1, we get an input state. 2, to prepare the cluster state. And this is a finite time process because there's a finite time circuit which prepares the cluster state. And the third step was to measure. This also takes finite time because I can do all these measurements in parallel. Because all the measurements are acting on separated sets of qubits. There's no problem doing all these measurements simultaneously, so that also takes finite time, doesn't scale with system size. And I've showed you that the output is the Kramer's one-year dual. So to create the GHZ state, which is what I started this lecture with, I just have to use the input state plus, which is a product state, so we can create it easily, essentially in 0 time. So I've given you a way where with 3 steps, all of which take finite time, to create a long-range entangled state. The surprise here is that we could not create this long-range entangled state without this measurement process. This is long-range entangled, which means that it takes, in thermodynamic limit, infinite time to prepare using simply local unitary operators. But taking advantage of this measurement operator, measurement property in quantum mechanics lets you prepare it in finite time. And I told you that I'll briefly comment about the general measurement outcome. The idea is that in that case you can do the same thing, but like the bell pair creation, there's some post-processing involved. So the post-processing will be a local unitary operator, which you can still do in finite time. So even with general measurement outcome, which is what happens in the lab, you can create a GHZ state in finite time. The non-trivial aspect is the post-processing, which I have not discussed, but that's also a finite time process, and it's very easy to figure out if you want to write down it dynamically. And yeah, that's the end of the talk. Hopefully you were either interested in the quantum information part or some of the physics I talked about. So thanks for coming. If you have any questions, I'll stick around.
Okay, sure. I'll just take that.